protons came in. Without light, we had protons here, equal protons, and nothing can happen. So because of the light reaction, protein, and as soon as the protons came in, then there's a gradient. This is what the Mitchell Nobel Prize for. There's a gradient, chemical gradient, more here than here. And therefore, it's a driving force to take the protons from here to there. Okay, so that when that happens, then ATP. You see it? Maybe. I am very much interested sure that I explain things. I can only explain things as much as I know. Yeah. But do you see what I'm saying? That it doesn't matter the space where it is produced is not the important thing here for the chemiosmotic theory or ATP. It is the total gradient, and it is that gradient, according to Mitchell, Professor Nobel, is that gradient gives the energy for the ATP synthase to rotate. I mean, it rotates. So this energy, the chemical energy, is converted into mechanical energy and into rotational energy, and the rotational energy is back into chemical energy. That would be one of my lectures. I hope I get to it. Okay? Yeah.
As we have seen that PH2 is present in the aqueous region of the ground, and PH1 is present in the non-aqueous region. Is there any reason behind this location?
I am very sorry that the hive plants did this. Because the cyanobacteria and many algae have no such problem. They have all it is an evolution of the higher plants which wanted to stack more and more chlorophyll. They came from the land, they came from the oceans. When the algae came from the oceans, I don't know what they did. They had no problem with CO2 or whatever, and so they wanted to just stack up. So they stacked up like that. So what you see is God or something behind it? I don't know. What is the reason? They are not more efficient than many algae, which have a photosystem 2 and photosystem 1 all spread out. I'm not giving very clear answer to you, but the point is that there is efficiency, there is regulation. So they have photosystem 2 out 1 to 1, and they don't need to be next to each other. And the reason they don't need to be next to each other, because the cytochrome B6F is in the middle, and it is everywhere. So it takes the electrons and the protons go in, and then it gives the electrons the plasticinin, and the plasticinin is mobile. It moves physically. It diffuses the photosystem 1. So it doesn't matter. It matters only the diffusion of plasticinin with microscope. So it so happens, the question is, are they more efficient than algae? I don't think so. But essentially, at high light intensity, it's all governed by enzymatic reactions and so and all that. Right? It's only one. No water oxidation. There's no oxidation.
There is higher, there is more regulation than in comparison to the photosynthesis.
Of course, there should be, because you have more things to regulate, right? Bacteria are simple-minded folks. I worked on them a little bit, but I didn't like, because this is more fun. Okay? All right, so. Good.
So sometimes plants get excess light.
Good question.
How they protect themselves?
Yeah, well, that's exactly my volume 4, which I bring every day except today. But one of the slides that I showed was I'll answer your question before this. What they do is that too much light is there. Okay? So it means you are in an excited state, and what you will do normally, where oxygen is everywhere. The O2, that they will give the electron to O2, will become O2 minus, and it's very damaging. It kills everything. So the plants have evolved to protect them. So that should be one of my lectures, I hope. Time to lecture on that. What they do is they, instead of doing photochemistry, they lose it as heat. Now, not in themselves. There's other carotenoids, sylvaloxanthin, anthraxanthin, and zeaxanthin. Sylvaloxanthin becomes zeaxanthin, and zeaxanthin then picks up this extra electron onto it, and then it loses its heat. So that's one of the hopefully to answer your question. Okay? Everybody good? Okay, so let's see. So the whole idea was to be able to do the Z-stream round. And how do we do it? So please align yourself in this way. So now I can direct you, but we can have a break. Anybody volunteer to be a director, or I can help? And then somebody else does the direction together. I think you need to get together to do it. So let us say, why don't you try to sit, let's say, and, no, because we don't have trees in town outside the road. That's not beautiful. That's right, otherwise I'm leaving out. Anybody here at some who have sent me an email? Because there are several people who have responded by email, actually replied. And I just, no, nobody did. All right, so let us say, let me just, so we have, let's say, 3 quarters, and it's very difficult to normally, when I talk, Nirvana had a ladder, so I could go up on the ladder. So you have 50 seconds. So both of them, so as soon as the light comes, you both go up, like, up. So fish, huh? Kabul? Lights. Light ठीक है, अब हम light वो cycle चाहिए, बस ऐसे बोलेंगे. So that process. So when we do the drama, we can do both at the same time. But just for you to know that both happen. You saw that movie, that nice movie, right? Remember the singing movie? So go to excited state. So let us do the photosynthesis process, as I said, takes place in temperature in 150. You have the high electron, and then let us say UV P680 and UV P580. And as I said, there's more complications. There's another sometimes participating. But let's say keep it simple. So you are there, and it's lower, so you transfer the energy. And then you got the energy, you got the electron, not energy. Now you have the electron. So you are reduced, let's see. So the electron went up, that's it. But it didn't come down. If it came down like that, now be first. It would lose energy. So instead of falling down, it was given to you. See, you were reduced, and that's the measurement peak. And then you got the electron, and then what do you do? Within 200 picoseconds, so this was 3 picoseconds, within 200 picoseconds was the QA. Now this QA is a totally bound. You cannot leave any place. It's going. It becomes Q mine. There's a cluster command 9 that's reduced and only can take away. And she will hold it forever. Because it's very tightly bound and its environment is such, chemistry is such kind of. But then it gets within about 100 microseconds. Now she is very cagey about this electron. She will hold it, will not give it to anybody. And the lifetime of CB is very high, if not enough. So now, so we have forgotten the 36 hours. So now the second electron. And then I got 2 QB. And all the balloons will not go from so now nothing, she can't do anything. So one proton comes in, but for the stabilizer. When the second proton comes in, then it becomes TBH. And then goes out of the system where she's sitting outside and becomes plasticonol. And then another plasticonol molecule comes in and sits in her place. She may be the same one, but no, really, because PQS2 has to lose the proton and the electron. So that is, now, where does the bicarbonate come in? This in the proton, the bicarbonate is necessary. This is my word. Comes in to give the proton through other amount. And then once PQS2 goes and goes to cytochrome B6F complex. Now how much? This is my first was 100 microseconds. The second was about 400 microseconds. This was all done in Urbana by the group of Philip Ross and many other people in the Netherlands. I'm afraid because of the mistake to forget. So whoever is listening, please forgive me the names. All right. So then this comes now. When we will discuss next time how the QB and cytochrome B6 function, that's more complex issue. However, the simple point is that there are two electrons. So one electron is given and she goes inside the molecule. And what is inside the molecule? Cytochrome B. So 1B, 1B, another electron is put in there. The other electron comes in and it goes to the risky iron sulfur center. And from the risky iron sulfur center, so and then we can read them. So you see, it's not just one electron. So one electron is, there were two electrons, but one at a time over there. Here, there was a 2 electron gate. So how much time? What was the slowest? It was the time, the slowest reaction was the plastoquinol going and doing all these things. First, it's diffusing from here to here. That diffusion will slow down. That is a millisecond process, 20 milliseconds. And that's the slowest step. And the oxygen evolution is first not taking place. But other steps are going on in parallel. I cannot be doing all the things simultaneously. But water oxidation is also going on, actually, but not with 2. It's only still the S1 went to S2 to S3. You need more photons, more electrons. So anyway, so that was about it. Yeah. So now, what is the other side? So we'll go. All right. So basically, then the same. This P680. P680 is remember only the molecule. When you talk about, I would say photosystem 2, which is P680 plus 6 other chlorophylls plus many proteins, CP43, CP47, OEC33, 18, 9, and the whole complex that sends pictures. So that's it. Okay, so now we have 2 electrons coming. So now let's do the photosystem 1. So now here everything is 1 electron. So you are. So in the supposing you are the P700, supposing you have to be active P700, sit down, please. So the P700 was excited, okay, P700 plus became, and then transfer the one electron. Yeah. It's not the same electron. The other electron was coming from there. So the plastocyanin, supposing you were the plastocyanin, you physically move to give the electron. So basically, that was a slow reaction, but still in microseconds, 400, or maybe some minutes, 1 minute, 1 minute. So now, when the P700 has passed on to A0, and this also takes place in some picoseconds. So this process was also in picoseconds. And the Russian group, Shuvalov, I have a review, and it is on the thing with Shuvalov group. Please read it if you would, please. So now this, you are, whatever you were. You were both P700. No, you were, so you were A0, and then you transfer to A1. And all these processes are very simple electron transfer downhill from A0 to A1 to ferredoxin FX to FB, FA, FB, and then to ultimately to NADP through the enzyme ferredoxin NADP. And all those things are in microseconds, milliseconds, nanoseconds. So now we have, so let us suppose you are the NADP plus, and so you first got an electron, one reaction, so you became NADP. So it is NADP plus and become NADP. And then the second electron is become NADP, and then you are fine. You made one NADPS, but there is another fellow. You could be the other NADP plus, and then you will also get, so you will make two NADPH and two NADP plus, the whole system. So the bottleneck still is, so basically this is a very simple-minded way of explaining. As we've seen at the time to repeat, it's not here. I have a slide I use. I don't know, it's already there in one of my lectures or not, but I will make sure that that slide is there by itself. And which has all the time picosecond, 200 picosecond, microsecond, and millisecond, and then you have all these things in the microsecond, and then here you have again a picosecond, of course, it's simultaneously, and then sub-picosecond, nanosecond, microsecond, and time. So this is how this goes on, and when four of these gone out, we have 1 4 through the manganese complex that I described to you. So now somebody is asked a good question. Of course, the system has to regulate up to know how much ATP and NADP is being made. So the cyclic, not one cyclic, but in Japan, at the paper in Nature last year, there are actually two cyclic pathways. Go down and it's going around and around and getting the energy, so therefore you can have protons and more protons will make more. That's how you make extra ATP through the cyclics. I don't know, because the whole question, yeah.
So from that cytochrome B6F complex,
Yeah.
you said that from QBH2, the two electrons were given to
Give
different.
all first. I don't know. Yeah, go ahead. Yeah.
From the QBH2 molecule, the two electrons were given to different entities. One is the risk iron sulfur you said, and another.
Right. So we can discuss that right now if you want. I'm getting lost in my time. So that's let me explain that. Water. Okay. So the question is very important because how the cytochrome B6F complex works. So you got, let's say now we just focus on the cytochrome B6F complex. Okay, sometimes it's better without the slide than without that. Yeah. So, so let us say so I bring so the PQH2 gave one electron, then so where? Yeah, it is like this physically. So you see the electron and see it's like one cytochrome B. And this electron, the second electron, goes to cytochrome and so now what? What to do? So just to know the cytochrome B has an extra. So every time there is a whole chemistry has to do with thermodynamics, energy, as well as electrostatic, the charge. But she has an extra charge. So this is sitting, and this is the outside, this chromosome. And I don't have another proton. We call this proton. So because she transfers that that electron to a plastoquinone sitting in the membrane. Okay, so that electron is gone. So she is now PQ minus. The outside says, negative charge, boom, a proton comes. So she has one. Now, when the second cycle comes in, she gets another electron, and she only has not two yet because it's PQ. She can have PQ as two. So this one goes and picks up another. So that's why when in the pictures we show the cytochrome B getting protons from outside, which is okay, but they're left out the protons in this diagram going to PS2, which was before protons were PB. So now she's become CQS2. What does she do? She moves physically to the other side where she can PQS2 can bind, and does the same thing that the linear electron produces. And so this thing goes on and on. The cycle goes on and producing ATP, the proton, which is what happened. He actually gave the name Type2 cycle, like this system. So that's basically, we can, since we're not using slides, we can also talk about ATP synthase without slides. Maybe it's better sometimes, right? Any other questions? Is that, I want to feel you are satisfied. I cannot satisfy all questions, but some simple questions. Now, how does the ATP synthase work? I will bring the slides. Go from the keypad to ATP synthase. So let's discuss, but not immediately. First, we'll talk about fluorescence, and I think fluorescence? No? Okay. And Deepika is generously, kindly making fluorescence solutions, and hopefully in an ultraviolet light. In Kataka, I went on a motorcycle to get ultraviolet light. So basically, what is it? How many Nobel Prize? Remember? Of course, there. Otherwise, you look at my lecture. One, of course, Peter Mitchell for the idea. Right, but who? Paul Boyer, John Walker, and then recently, Harry what? No. No, they didn't get a Nobel Prize. That's Wolfgang Junger and Kinoshita in Japan. We'll talk about his work. By the way, he had worked in Nirvana. He worked with Professor with my wife. So let us look simply at the so you all are so there are two things, F0 and F2. And the F1 has 3 alpha, 3 beta, and this has many. As a CU. So when the proton comes in, it binds to a specific place, and this binding at a particular amino acid in one of the units, and this changes its energy such that it rotates. Rotation. Okay, so when that rotation, there is what is called rotor and stator. So that rotation is taken into the alpha beta, and then they rotate there. Okay. So basically, the whole thing is that the chemical gradient is converted into mechanical energy through rotation. And how was the rotation proven? And I have slides on it. So one of the scientists in Japan, and then also Wolfgang Junger in Germany, they put a filament, active filament, on the top of the very ingenious thing on the top of the enzyme, and they could see while they ran the gradient, they could see that the filament actually moved. So the rotation was proved that yes, indeed, rotation. and all the details. Did I bring more slides today or just those two? Yeah, can you show what I have? So there was a water oxidation, we saw that. Okay, you can click on the, no, we just see what, so we have the diamond tiger, this is my review, you can make it bigger. Alright, anyway, can you make it bigger? So you can, so they cannot read. Anyway, so it is with you, and I would think you would like to read it. So you can move the pages. So that you can see all the pictures are taken from this review. That's the key. And it gives the source. So I was unable to give you the source for that report. So all the sources are all my students who make it first. Okay. So you have that, and please you can download it and read it, and hopefully somebody will talk about it. Take it. Is everybody ready for tomorrow? Who are the four or five people? Is anybody here who is talking tomorrow? 9 o'clock? Are you? What are you talking about? What is your name?
Anu.
Huh?
Anu.
Anu. A-N-U. Okay. What are you talking about?
The artificial.
Good. No, but which a special paper? Or? Okay. Anybody else? No, okay. So that's really bad. We will strike, so it is strong. Because unfortunately, what happens to everybody does it in my life or death. Sad what is happening. Somebody said, don't say it because you're being recorded. I'm not making any statement. Whatever it is, it's sad. That's the best. Okay, so please ask questions or whatever. I mean, I can go on and talk about the other sectors that I didn't bring in, or we can go over this one. So I didn't expect to finish so early because I was expecting the whole class, so to do the whole week. So if you want to think about, somebody needs to take leadership, collect everybody, because otherwise it would be a fiasco last day when we were going to show those things. And I can tell you, I am not the one who ruling the list. It's you who have to see the molecule and read the literature and to see which molecule you are, and you can either wear that colored clothes or you can know what plasticine it is, the copper protein, and what kind of thing. The P680. So basically, so basically, you need to have fun with it, otherwise it's and so you need to get together with everybody in the class. You have to have meetup and see how you can meet and have fun. Otherwise, and again, as I repeat, you are welcome to ask questions. I know a little about certain things, but I don't know. But I will be very happy to answer. But one thing is, whoever is coming, you have to write one page. Remember, everybody has to write one page. That's a good exercise. So one of the things in learning about being a scientist is that you have to speak, you will speak, you will talk, and that's why you will give a talk. Then you have to be able to write. That's why you discuss on one page, and you have to know things, and that's why they finally can. Okay, and with the presentations, we consider the quiz point and the final exam. So I'm sort of done today. You are welcome to have coffee with me or tea with me, but I can talk more. I think you have enough. So basically, 4 electrons of this have to be there. you have this list too. So, anybody have anything else to say? Did you, okay. No, no, please. Whatever the class is, that was, I kept it to the end before the. So the question is, what on earth is the library for? And many people have been writing to me, yes, sir, which I talked about. Dear Govinji, or if you don't feel comfortable, you can write here. Somebody said respected them. Yes, okay. You must respect it, but that's okay. I will accept the criticism. I want you to recognize that the library, in order for one to go ahead in science, it is essential to be able to read literature. Today, unfortunately, many books are very expensive. All my books, $400. So basically, you either have to find a book somewhere, I won't say where. You have given me my home, but you have to read it and find it. A, in Google, PubMed, also on your own library. I can find, I don't book in the library, but I most of the important journals. And your library also has many important journals. And therefore, all of you should be using the library every day, at least an hour, to find what is there for you to learn and be ahead of other people and ahead of. So basically, I requested for Nadi to see if he can show you how you can, if you don't know. And I feel many of you don't know, because I found things on your own library and downloaded it and sent it to you. Not yes, somebody else. Okay, you are the speaker.
So you have the JNU e-library, and you have JNU e-library, and there are different search, in which you can search for books and ebooks as well as articles. There are many full text articles.
How do you get to the
Just if you go to Google and type in JNU e-library, this is the web page, library.jnu.ac.in.
Library dot
lib.jnu.ac.in.
lib.jnu.
And so at the home page, you have different services for like articles, books and ebooks, and JNU catalog, and as well as the thesis of for me. So, and Anushi has artificial photosynthesis. And you can search for full text.
The place for full text.
So we have about 12,000 results for artificial photosynthesis. And here you can see there are academic journals and here PDF full text. So you can download either directly from here or they have source links as well. So if the full text is not available on the library here, they have a full text link source. So you can download PDFs from there. And so that's basically it. And if you need books,
Supposing you want to look for some author.
yes. So there are.
Is there a place to type in author's name?
Yes, this is for keywords, and you can like change it to title, change the title of the paper, or author.
That's what somebody was saying.
So if you type it,
Did you spell it right? It's not the I. Govinjee, right? Yeah. Maybe you have nothing. The reason I warn you that I may have nothing because they delete my name from most papers. But there are some papers.
Yes. There are 648 papers.
Well, they're not all research papers. But you can click on that, just the first one, Alexander Krasnovsky. Krasnovsky is a, can you get the PDF? But anyway, since Krasnovsky, the discoverer, was called Krasnovsky reaction. So let the chlorophyll, when he put light on it, we found we said P680 is oxidized from P680 plus. The P700 is oxidized. How did people make the decision? They made the decision because a chlorophyll solution, when it is oxidized, changes its absorption spectrum. And my professor, Eugene Rabinovich, discovered chlorophyll oxidation and published in Nature. Krasnovsky in Russia discovered that when he puts light on his solution, chlorophyll is reduced instead of being oxidized. With a different chemistry, a chlorophyll in solution, depending upon the environment, can be both reduced and oxidized. So that reaction was known as Krasnovsky reaction. So initially, when the two light reactions were discovered, this is a kind of history, for private history, that some people thought that one photosystem chlorophyll is oxidized and the other is reduced. And Bessel Koch, one of the major discoverers of P700, said P700 is oxidized by one night one, and then it is reduced by the So his explanation earlier in 92. So the Krasnovsky was okay at that time, but later it was discovered that both are. Okay, you go ahead. Sorry. I just remember this little history. I've written about Krasnovsky. I went to his 100-year celebration in Moscow.
That's
Oh, that's it. Oh, okay. All right. So please use it. And to when those who are not here, maybe you can send all of them an email or something to request them to look at papers in what they're talking about. So they are not going to be able to say these things in 10 minutes or so. Like I'm not able to say these things. I have read thousands and thousands of papers, and mostly forgotten. But at the same time, I have read them to have some feeling about what exists or what doesn't exist. Right? So basically, it's a good idea that everybody gets to know how to use the library. And if anyone fails to find what they're looking for, I am happy to talk to you or help you. But you have to write specifically. Like somebody is that's another point. Somebody send me, I will send you a link. Now, what does that mean? Which means I have to click on the link in order to find what they want. So I wrote to one person. I said, please send me the reference. Of course, I found the reference, and I sent that person the paper that you wanted. But if you ask somebody, you have to check that you cannot find it through Google, through the PubMed, through the JD Library, and then you can write to me, because I can find it for you. Not from the Google, because if you already look, I find it from the University of Illinois Library. Because many papers, some papers, I should say, may not be available in the JNU Library, but may be available, especially old papers, in Illinois. So I'm really happy to help. I would like to help, but I also like to learn how to make best use of it. Okay, anybody else? See you tomorrow, but please find those other folks, request them. You know their emails, and then you can another email, but they have to be here 10 minutes before 9 o'clock. I hope you already coming tomorrow. So that they have to upload their presentations, and they should be numbered 1, 2, 3, 4, so we can easily my name alphabetically. Okay? You were the first? Okay, so you know. Do you know those other four?
Yes.
Okay, could you please help us? Good. And tell them to be happy. Because that's a good chance to make friends. By telling them exciting things and address, right? Good. You need me? Well, when? Now?